So part 2 of chapter 8. So we'll move on to propensity score weighting approaches. So here's the model. So suppose we have, this is a parametric model, logistic regression, but y is missing, right? So y is subject to missingness. So it's not really easy to fit a regression model, a logistic regression, because you have a missing data in the covariate. And another more difficult problem is that you have a semi-parametric response model where you have a, so basically you have a parametric part in y, but non-parametric part in x. So that's probably not really easy, right? I mean, you can see this is more difficult. But even the parametric model is it's not easy. So let's move on. Okay, so parameter estimation. Okay, so let's assume we have a parametric model, something like logistic regression, and then how to estimate the parameter? Two approaches: method of moments estimation or maximum likelihood estimation. So method of moment is the approach. First of all, you need so to make our life easy, let's assume we have a non-response instrument variable. So that simply, that is a reduced model, right? You intentionally exclude one variable to the model to reduce the number of parameters to estimate. So with that, Carl and Chang propose solving this kind of equation. So you have 3 unknown parameters and 3 equations. So hopefully, oops, okay. As long as, sorry, y. So as long as you can have a solution, then under some conditions, so as long as you have a correct model, right? So if you have a correct model, then the expectation, so if you take the expectation of this guy under the x and y, right? If you take the expectation, then the given x and y, the only random variable is delta, right? So then the expectation of this delta is equal to the denominator. So you can actually cancel, right? So the numerator and denominator cancel. So it is 1 minus 1, so which is 0. So that means at least I mean, it's hard to believe that the model is true, but under that model, I mean, conceptually, this is provide a consistent estimator. So that is kind of an interesting idea. And then so we Wang and Xiao and me and Kim, we developed the idea of further and more generalize the result. So okay.
X2 is related to 1.
So okay, that's good question. So why we add one more parameter, right? X2 and P3y. So then if you do that, you put it here, you have a 4 unknown with 3 equations. So that you cannot really solve it. You have more unknowns than number of equations. So you cannot really identify the model. Okay. So what I'm saying, the identified model is you cannot really have a unique solution. Okay. So then if you cannot really estimate the parameter, so in the statistical approach, the first thing to consider is whether you can identify the model. If the model is not identifiable, then you are actually you cannot do anything, right? So MLE, for example, so if the model is not identifiable, then you cannot compute the MLE even. So you cannot do anything. So that is, so this is, you know, I know this is a strong assumption, but that is what we kind of accept to get solution, right? Essentially.
We use TML if we have more, we use TML if we have more parameters than the constants we have.
So yeah, so actually this paper is, so this paper so why we just use it, right? I mean, you can do more, any function of x and create the more equation. So that is the idea here. This is the simplest possible of just exactly identify the situation. You have a equal number of equation and unknown parameter are equal. So that is a just identified situation. So you see, we have three just identified, over-identified, under-identified. So under-identified means it's not really identified, right? Over-identified, you have a more equation. So that means you don't have a solution, but you can do something. So these two. So this is just identified situation. This paper, Wang et al. Covers over-identified situation. And under-identified situation, under-identified, we cannot do anything. Okay.
Over-identified situation, one of the solution will be to penalize the like no solution, but
well, GMM. So okay. So over-identified situation, we usually use GMM. Or empirical like it. Okay. So then see, you can, right? So the idea here is you can do many, right? And then natural question that you can think of is you can write it, actually put it as a class of it. Class. Okay. You put it as a class of estimating equations, right? You change B function. So if you change B, then you have a different equation. And you have an infinite number of choice. Then it becomes a class. So then naturally, so this solution to this, so we can, first of all, we use a subscript B to emphasize its dependency on the function bx. Okay, so this can be anything, but so that means this solution to this equation will be set at B because it depends on the choice of B, right? But no matter what choice, the expectation are all equal to 0. So the expectation of this main equation is 0. So that means the solution will be consistent, right? But the variance will be different, right? The variance will be, so then it is really a nice mathematical statistical problem, right? Among this class, what is the best B? What is the optimal choice of B? Okay, so that is something that we are going to consider. Okay, so minimizing the assumed variance of set type B. So first thing is to obtain the general form of the asymptotic variance using sandwich formula. Okay, so we'll see this is the form of the variance, and the variance form, asymptotic variance, will be function of B. Depends on B, right? But it's more complicated because, so in the usual IID case, right? In the usual IID case, you don't have this one. Right? In the usual IID case, because it's a random sample. So you just have but here you have some O function, and then O is the non-response odd. So OXY is this one. And then S0 is the score function of phi at delta equal to 0. So this is the, so S delta means you have a delta equal to 1 or 0, right? So you have a 2. So this is just a notation. So S0 is the value of S delta at delta equal to 0. And then what is the S delta? S delta is essentially the scope function corresponding to the to phi, right? So this is the basically log-like log density, log of the density function, right? The density of okay, so density of density p delta given x and y is Bernoulli. So you have a pi xy delta times 1 minus pi xy 1 minus delta, right? So from that, you take the log, and so then you have this one, and then take the partial derivative with respect to phi, right? Then so if you do that, this one is, so if the whole thing is algebra, you have a one, because it's a log, right? Log of pi. So delta divided by pi xy, and then plus you have a minus. So is it a 1 minus pi xy and minus, right? Sure, minus. And then set phi pi. So this one is actually you do this one, and then round the pi by round the phi, and then simplify. So then this guy is a pi times 1 minus pi over delta minus pi. And this guy is, turns out that pi, yeah, so that is actually this one. You don't have to simplify further. So that is this one. Okay. So now the only thing is to show this, right? So that we can actually use. So you have PV is what? Delta I pi I phi basically minus 1 pi. Okay. So your asymptotic variance, so phi hat is 1 over 1. Basically, remember the sandwich formula is what? The expectation of the round phi round u what you had b inverse variance of the u. So okay, let's do it this way. Variance of u hat b phi times, right? So something like that. So all you have to do is just compute the. So all you have to do is just compute two terms, right? One is the partial derivative of the expectation of partial derivative. The other one is the variance of the u hat. Okay. So So this one is expectation of the minus pi I square phi over delta I bi times sorry. Round the phi, round the pi I. Right, you have this guy, so like this. And then so from equation by 5, so if you look at this round phi round pi I is if you put 0, then S0 phi xi yi times 1 minus pi xi yi phi minus. It's just algebra. It's just this guy.
Jay, I have a quick question, sorry.
Go ahead. Yeah, no problem.
Yeah, so so in your equation 1, so you assume that the B is independent of phi, right?
B,
No. The notes that you write.
okay.
Yeah, in the notes you write is the derivative of
Okay.
the derivative of U over yeah, so you assume that the B is independent of phi.
No, I didn't evaluate this is a partial derivative, so I didn't evaluate the expectation yet.
Yeah. So if the B is also dependent on phi, so the partial derivative of phi should also involve the
I see. You mean this one? You mean the dependence on phi here?
right.
That is negligible because of the. So that's good question. So you can actually treat it as a known phi because the expectation is a product of. So my point, you don't see my so I should use. So this guy has a 0 expectation.
Okay.
So because it's 0 expectation, the randomness of phi, so you can actually ignore.
Okay.
You see what I'm saying? Yeah. So because of, so right, usually you can't, right? Usually you can't because you need additional. So that's very good question. So you actually have another, right? You have something like this, bi.
Oh, but the expectation is 0. Okay, I
0,
see.
right. So sorry, I shouldn't. So that's
see.
why. Okay, thank you. Okay, so so that second term is 0, so I kind of ignore it. So now we have basically, if you put delta equal to 0 here, as delta, then 0, right? 0, and so this one cancels. So that is essentially minus 1 divided by 1 minus pi. So that this guy is at 0 times 1 minus pi. Minus. So that is this guy. So that means you can actually say that this guy is minus cancels, and end of the day and delta expectation is pi, and then you have a O times P times S0 prime. I mean, if you have a prime. So that is the first one. And second one, you compute the variance. So the variance of this guy. So this part is relatively easy. You have basically 1 over n times the variance of due to delta. So that is pi 1 minus pi square times b prime expectation. Okay. So that is essentially 1 over n times expectation of O times B times B. Okay. So you got this one is this one. So that proves the this theorem 2.8.
There is another expectation working inside, right?
Huh?
Otherwise you cannot write the O.
O is just a function of x, y.
Minus pi.
O is just a function of x and y, which is the 1 minus pi divided by pi.
Yes.
So
And there is another pi in the denominator, which is like expectation of del given x1, right?
which are you talking about here?
Yeah, I'm talking.
So this one.
Yeah,
So
that equal.
so pi expectation of delta is pi. So
Yeah, there
pi
is another
cancels.
expectation of work.
So pi cancels, and then you have this one 1 minus pi divided by
Yeah,
pi, which is O, and D and S 0.
My point is, there is another expectation working inside that. Otherwise, you cannot just cut down the pi delta divided by.
Yeah,
pi.
sure.
Yeah.
So here you are actually right. You take the conditional on x and y, you take the expectation delta, and then write it.
Yeah.
So okay. So that is the first step. So we get this asymptotic variance in terms of B. And now this is actually quite interesting problem. So how do you want to find optimal B, minimizing this kind of formula, right? So that is so if B is scalar, so if you think that B is scalar, this is, you can easily prove that using some Cauchy equivalence. But but anyway, we'll see. So the answer to this problem is, the answer is that you can obtain this solution. So we're gonna show that soon. So asymptotic variance here is minimized at B star, which is this one. And this one is an expectation of O times S0. So this is not easy to compute. So you can actually use this E1 using y given x and delta 1, and then put delta. So let's see how to prove this. So okay. So here's a proof. This is a very useful technique, actually. This is kind of Cauchy equivalence, right? But this is a vector version. So that is. So that is the actually. I was actually, I proved it myself, but turns out that this is already published. The paper is in econometric journal. It's only 3 pages in the paper. So title is, if you, I found it very recently. A matrix extension of the Cauchy equivalence inequality. 3 pages. Published. That's it. No simulation, nothing. Yeah, Cauchy equivalence. So Anyway, that. Okay.
I have a question on page, I think page 7.
7, okay.
Yeah, because we just proved that, big B, is equal to expectation of, O times B prime. And here, I think we take, the conditional expectation.
I see.
Yeah, but B is a function
Over
of
X.
X, but, why can we take it out? Because we take expectation.
I see your point. So this one is actually OBB, right? But B is function of X, B is function of X, this is function of X and Y. So you can actually put expectation, so this is joint expectation. And then you can regard it as a expectation, marginal expectation of the condition expectation. So you can write it as a, oops, yeah. I cannot, so. XPX. Yeah, so then you can always write it as a O X and Y given X times BX prime, right?
So there is no randomness in B.
Hmm?
There is no
BX function as a function of X. So this can go outside. Okay, so this is function of X. So then conditional this is constant. So you can go outside.
So the first expectation is the joint, is with respect to Y and X.
So this is X and Y.
And the next
This
one
is
Y
X
given
and this is Y given X. Right? Okay.
Oh, first one.
Okay. So that basically take care of the, so anyway. So I'm not going to prove this. If you are interested, you can take a look at this 3-page paper. We're gonna use it, right? We'll use it to solve our problem. So first thing is to take the inverse in both sides. So if you take the inverse, then you can get this one, right? So this is what we want to use now. So how do you connect? So basically this is A inverse, B, A inverse. So that basically this, so this is B. So B is what? B is expectation over O tilde XX. B prime, right? So O tilde is the expectation of O given X. And this one is what? This one is expectation of the expectation B. Yeah. B times expectation of O S0 prime, right? Given X. That is A. So this is A. This is, so question is, if you use how to, so, okay. What is the right choice of B and X to make this guy is equal to B and this guy is equal to A? So the answer is, so we want, so B should be, what happened? So think about that until I charge this pencil. But this is So y should be linear function of b, right? Okay. So y should be O is a scalar, right? That's the only way. This is the only way, right? You can achieve this. Because you have y prime y prime is O times b prime. So this has to be this, right? So then you know y already. So then what is x? X should be O tilde minus half times O S B X. Oops, sorry. This is expectation of O S 0 given X, right? So because of this, because we choose this should be equal to this. So that means Bx has to be this, right? So that means we are done. Because we know the optimal solution occurs when x equal to y, essentially, times c, but c is constant. So that means we want x. So that means we want O tilde half E O S 0 given x equal to O tilde star B star. Because we want to find B, essentially. Everything else is given. The only thing we want to decide the B. So that means B has to be this. So we are done. So this is just move this. Okay. If you just move this, then O tilde is this one. So then it goes denominator.
And you're using this equation, like x is equal to c1.
Huh?
You're using this equation, x is
Yep.
equal to c1.
Right. So with the equality, because the lower bound is achieved value, right? That is the value, the solution to the optimization problem. So that gives the solution. Okay.
Okay, y02 reflected, 1/2 times this conditional expectation times y, equals to b.
So
Yeah. How do we, simplify x to O to the 1/2 times b?
you mean how get this solution? So we want this the cell in the center equal to B, and the right the red part equal to A. So then B is this. So that we want to equate y prime equal to O tilde PP prime. So that means we have to have this. No other choice.
I mean, but there's a expectation of O times, 0 on the left-hand side. How do we cancel that?
The expectation.
Yeah, the expectation of O times S0 given X and times Y. And how does that term becomes O to the 1/2 times B?
Why x transpose the whole thing is equal to b times the expectation. and we know B is equal to the vector Y. So the first thing is the Y times Y transpose. It has to be O times B transpose. So Y has to be O to the power 1 to the power half times B.
Because X, I know that X equals to that things times Y. I'm just wondering how the rate comes to, right this side.
Then you're in two separate equations. And X equals to something and Y equals to.
Yeah, I know, but, after X equals to that things, we simplify it into O squared times B. How the transformation. Maybe,
So that equation.
Hmm?
14.5 B is equal to that. How this equation.
Where are you?
Sorry. I think that is expectation of that times Y.
Yeah, there you're two separate.
Sorry.
Okay. Okay, let's move on. So. Okay, so we found the optimal solution, right? So that's very good news. Because that's not a trivial problem, right? If you think about that, we are interested in solving this kind of a class of equation. And we are now able to obtain the best one, minimizing the asymptotic variance of the solution to this class, right? So that's very nice result. And now that's not the end of the story. So now let's reflect. Okay, what is going on? What is exactly this solution is saying? The solution, what this solution is saying is that it achieves the lower bound, right? I mean, it's a solution. So what's interesting about this phenomenon? Basically, the whole thing makes X equal to Y. Right, the lower bound is essentially we use this X equal to Y. So that means we make A equal to B. Right? So we basically solve A equal to B essentially to obtain the solution. So that is actually this one. You can easily check. So that is actually so. This is B. This is A. And so instead of doing all this Cauchy-Schwarz, you can directly solve this. If you can. It turns out that this is not really difficult to solve because you can actually move one, right? And put it. So my point is that, so how to solve this in terms of a B, where you can actually see inside that what is core is you do like OS. I don't know. So end of the day, what really solves what it is really solving is B S O times S 0 minus B given X. So this one, we basically the optimal solution try to make this guy equal to 0. So that is interesting. So A, right? A equal B can be written as something like this, which can be written as this, which serves the solution. So you don't really have to. Turns out that you are not. I mean, at least the solution is just solving this A equal B equation. And then what is A and B, by the way? A is this guy. This guy. B is this guy. Right? End of the day, you are just essentially solving this one. And then this one is actually Bartlett identity. Remember, the second by Bartlett. So remember what is the nice thing about where the Bartlett identity comes from. Remember in the very beginning of the class, chapter 2, when we introduced the score function, right? Score function satisfies Bartlett identity. So that means the optimal one, right? Optimal Eastman equation should be very similar to score equation by nature because it achieves the lower bound, right? So that is actually, so it's not only the score function, but also the optimal equation should semi-parametric. So that is the basic behind the semi-parametric score function theory that I plan to cover next semester.
Can you please explain that?
Huh?
Can you explain
I'm sorry?
why does it matter?
Okay, that's a good question. So, well, yeah, there's some more details, but see, what is, so this one, okay. We have actually on phi, right? I mean, we have an estimating equation, estimating function. And then we start with this, right? So we start with this. So that from this, we can actually obtain, what we can obtain is this is actually scope, originally this is scope function. So if you remember this, if you are more rigorous, this one, you have an integration, right? You have an integration inside. So if you take the pattern, then you have something. So this is a function of phi here, right? So you have two things, and so you just change the this is the original, right? So this is bad. The nice thing about this Bartlett, I mean, this result basically says that you can kind of treat this guy equal to the scope function, even though I don't know the scope function. Well, so why, and by the way, what I mean by semi-parametric? So here, actually, this is all about X and Y and delta, right? The whole random variable is X and Y and delta. And so we are actually have a joint distribution of X and Y. But phi is only part of the joint distribution. So you have a sub parameter. So in the joint distribution, you have a full joint, right? And then parameter of interest is phi. And the other parameters, sometimes called noises parameter. So phi is the parameter of interest, and then the other parameters. So the other parameter you don't care. So that is called the noises parameter. So parametric model So in the parametric model, the noises parameter space is finite. But here, we allow this parameter space to be infinite. Then it's tricky because then what I mean, how to, so then the meaning of this one becomes slightly changes. So it's kind of a projection. So this efficient score function is a projection onto the orthogonal complement space of the infinite dimensional parameter space, which is too much for this class, but hopefully I can explain more better in the next semester. Okay, so that is actually quite advanced area, requiring some projection, all these techniques, but I hope, but that's very, these days, if you want to publish in a good journal, then you need to have use that technique. you know, it's like inflation, right? Inflation. What do you mean by inflation? You have to pay more, right? To same thing. Same thing. I mean, you have to pay more techniques. I mean, knowledge in order to publish to the because essentially inflation. So you have a limited outlet and you have more advances coming. So then, so anyway, so nowadays, if you want to publish in good journals, then all these semi-parametric techniques will be very helpful. Okay, let's move on. So anyway, this is kind of intuition, right? I mean, so what exactly means by optimal? So it is trying to achieve the place where we have the partial derivative equal to the so where the Bartlett identity holds, that magic happens in that boundary. Okay. And so now that we know the optimal
Jack,
form, yeah.
So Jack, I ask a quick question to confirm. So
Okay.
here you are not saying, using the optimal B, you get the same efficiency as the score, right? So you are not saying that, you're just saying it's comparable to score.
Comparable, right.
Okay,
Well,
but using the score is actually more efficient.
actually, I plan to address that. So it's a slightly tricky. I'll cover that soon. That's a good question, but I have an answer later.
Okay, thanks.
So yeah, that's very good, reasonable question. But so okay, well, the short answer is I only consider this class. The class I'm considering is this class. So this class does not cover the class for the score equation. So score MLE does not belong to this class, right? MLE. So then we'll move on to MLE soon. But so the optimal MOM estimator only developed under this class, and under this class, at least the optimum happens in the same way that score function is doing, right?
Yeah, but Jay, how about so the B does not cover the score functions, but how about you take the projection of the score functions to the space of X?
So I have a question.
Well, I think that is beyond what I can answer right now.
Okay, thanks.
Okay.
I have a question. So you're saying that MLE is not within this estimating equation. So it is a general class of estimating equation. So why MLE is not there?
ML is not there. So I'm gonna explain why. So actually, I plan to cover MLE. So this is MLE. MLE is here. It doesn't belong to the rational moment class.
Oh, it is a natural moment class.
Yeah. So it's a different class. Okay. So we'll move on. We are. Okay. Okay. So we wanna. So this result theoretically useful, but in practice we cannot really compute it from the data because it's using the conditional expectation, right? So in order to estimate it, we need to use this equality to estimate it from the sample, from using the respondent. Okay. So F1 y given x delta equal to 1 is the response model, so respondent group. So this one, at least we can conceptually estimate this conditional distribution. So let's move on. So that is the basic idea here. So you can do either non-parametric, or you can use parametric as a working model. And a nice thing about parametric approach is that if the model is correct, then this is optimal. if model is incorrect, then your estimator is incorrect estimator, right? So if the model is incorrect, then this one is no longer, B hat is no longer consistent to B star, because you have a wrong model, right? So it doesn't go converge, but this is a still function of X. Okay, so then it belongs to the original class. So still it belongs to this class, so that is consistent. That's the one thing. Okay, now this is more challenging problem. Okay, so we are not really interested in estimating phi. Phi is just a tool to estimate theta. Okay, so
we need to calculate phi and using y, because y is suffering from disease. And we don't have missing at random. So
Right.
if we use complete cases to compute phi star, will there be any bias?
So for complete case, we observe all delta equal to 1. We don't observe delta equal to 0 of data. So how can you solve? Right? We cannot really apply its coefficient.
But in that case, in page 12, when we are trying to compute phi, so we need y here for computation. So we need
Yeah, delta equal to 1. Delta equal to 1, we observe y.
observe y.
Right.
Why is suffering from non-ignorable weakness? So will that introduce any bias?
So So okay. So we use this equality first. So this is in terms of the original distribution y given x. This is the distribution y given x and delta equal to 1. But we use this equality. So we are not using estimating this. I mean, we use first this expressed this way, and then estimate this component. Okay, so let's move on. So this is actually a key result. So we are interested in mean of y. And so far we discussed how to estimate the phi, right? Phi hat, so use it, that's the moment, whatever, we estimate phi. But now we want to use x, right? So then we can actually consider add mx as a free function. You change over m. So you change over different mx, then you can still unbiased, right? This is expectation of delta is cancelled, and m cancels. So no problem, right? And so you can. So this is unbiased, regardless of the choice of mx. So then naturally, what is the optimal m? So optimal phi, we know how to use it, right? We use the maximum moment. So that's taken care of. Now, what is the optimal solution? That is actually a difficult problem, because if you consider this class, this is easier. So if you consider this class, linear class, I mean, if you know mx belongs to linear function of x, and beta is unknown, that's much easier problem, because beta is finite dimensional. So basically, if you know this functional form of the mean function, then you can write it as you can write the variance of this estimator as a function of beta, which is quadratic, and so you can differentiate. So you can do something. But this one is a functional, right? This is any function of x. So this is a functional optimization problem. So this is much difficult problem. Okay. So this is, again, this is a class, right? This is class of estimators with the varying m. And then the answer is, so the optimal solution is this. So this is the optimal estimator, optimal solution. And now, for now, if, suppose MAR, if MAR, then OXY is a function of X. So it's a free of Y. So then it can go outside. Right? It can go outside and cancel out. So O will disappear. And then this will be just Y given X, which is the result that we already studied in chapter 7, right? So we studied this in theorem, I think theorem 7.1 or something.
So since it is not under MAR, so that's why it will come any function of it.
Yeah, any
Because
function
I-
of X, right?
It is not expectation of Y.
So yeah, I mean this is the so we assume parametric model, but nothing else, no other solutions, right? And find the optimal solution. Okay, so how
So
to
Jay,
yeah.
if the response model is not correct, so then this may not be the optimal, right?
Sure, no, right.
Okay, okay.
So yeah, okay. So the proof is turns out that not really difficult. I mean the paper is published in Annals. It's very difficult to prove, but the idea behind is much simpler. But to impress the referee, we need to write it very rigorously, right? So in the teaching, so good teaching is long story short. It's a good teaching, right? Research, short story long. Then, right, if you write prove something 20 pages, then people will be very impressed. Wow. But if you prove it only 1 page, then well, maybe it's easy, right? I mean, anyway.
So it is the secret of research.
Huh?
Secret of research.
Well, I can do both. So it's better to be able to both, right? You can use left hand and you can use right hand. Be ambidextrous. Okay, so let's consider the case when P is known. So that should be easier. So then that means so previously we have two nuisance parameter, right? P and M. But now let's assume that P is known. Two parameters known. Then we can just fix P and write it in terms of M, right? And then all we want to show is this one. So you want to show this. And then using the argument that the decomposition, right? You can write it, you can write the variance as a something variance and then covariance, right? Covariance. So here, basically you have optimal. Here you have M minus M star, and then you have a optimal M minus M star and M star, essentially. So this is and then, so showing this one is equivalent to showing the covariance issue, right? Is that we already discussed before. So let's just accept that this is what you want to show. So then let's move on. Then turns out that this one is using the correct model. This is what you get. So that means you're now taking the expectation. So the expectation, so all you have to do, so this is a function of xi, yi. This is function of x only. This is function of xy. So this guy in the middle is no longer a function of x, a function of y. So you can just take the conditional expectation. So that means, so this one. So that is exactly what we have, right? This 10. So 10 is essentially this one. So then pi is known case. It's a relatively easy. And then, okay. Maybe this is a little bit, so actually this is, you need to actually work out, if you really want to show that, you need to work out what the form of this, but I kind of do not want to repeat. So you use this one, right? So you have this one as a function of m, and then you have put m star side and subtract, right? So then you get basically this one will be something like this. Something like this. So then, and then use the others to compute the, so that this is conditionally unbiased to 0, so that the variance covariance term is relatively easy to compute. So there's some lot of computational details, but probably it's okay. Probably too much, but anyway, this is the basic idea. And now, if you want to move on to the unknown phi, then remember. So remember what is, we have this PS estimator at theta hat, right? So this theta hat star is the optimal one. So then you remember when you use MLE, we can view it as a, so P hat can be viewed as a projection onto the orthogonal part of the score function, right? So this is basically what we are doing here. So it's a kind of projection onto the orthogonal part of the UP star. Okay. So then, and then, by the way, the form of the U has star, P star is something like this. Delta I minus pi I minus 1 pi star, right? So then the projection onto this orthogonal space is actually just having kind of adding, I mean, it kind of, okay, computing the regression. So you have basically this guy comes into part of the additional covariant. And then turns out that, so you have this kind of gamma star, but because of the, if you choose M star in 10, then the expectation here is 0. So that the gamma star, gamma M star is 0. So that means the effect of, so under the optimal choice, the effect of using the p hat disappears. And so that actually create the so end of the day we get some a 0. Okay. Well, this is, I don't think this is easy, but easier than the paper at least.
Jay, can you do the previous page? So here. Okay, so you say that the coefficient equal to 0, so the gamma equal to 0. Okay. Okay.
Yeah. Okay.
Okay. Yeah, I will look at the proof in the paper.
Yeah.
Okay, thanks.
Yeah. But this is easier. Anyway, so the main thing is that this is another interesting problem of optimal estimation, and the solution turns out to be optimal regardless of whether phi is known or estimated in an optimal way.
So Jay, is this only valid for phi estimated as the optimal phi that you just talked about?
Yeah, right. Yeah, that's good question. Yes. So this one turns out that this is only true for optimal estimation for phi hat.
Okay.
Okay. Well, yeah. Could it be actually optimal m hat probably is. So if this B is not really optimal, but still we can get B star gamma 0, right?
Right. So because all
Yeah,
the
right.
phi hats are consistent, right? So
but if you I think I see your point, but this unless if you're not really doing optimal, then you cannot really achieve this equality, I think.
okay.
But anyway, let's move on. So that is a little bit complicated, but the ML maximum likely estimation is conceptually easier. So basically, we just compute the observed likelihood, right? So this is basically the likelihood function as a function of a phi, and compute the observed score function. Then you end of the day you get something like this conditional. So you want to compute the conditional expectation of the score function given x and delta equal to 1, delta equal to 0, right? And so this one, how to compute this? Well, the classical approach is to use a parametric model for y given x. So that is the classical approach, but that turns out to be some sensitive to the. So if this is not really correctly specified, then it's not really robust. So that's one way. Another approach is use F1. So two choices. One is the use F, right? This one is the classical choice. The new choice is Fy given delta equal to 1. Then you can still compute the conditional expectation using the other function. And this one is actually, so then the argument is that F1 is relatively, you can easy to compute. At least you can validate from the observed data. And so basically we can write it this way. So y given x delta equal to 0 is y given x and delta equal to 1 times the I and normalized. So that is and you originally in our paper in JASA. And so using that, you can actually have a two two estimating equation, two different ways of computing. So the equation 14 is the original equation. So basically, this is a mean square theorem, right? You use a mean square equation. The conditional expectation of the S given delta equal to x and delta equal to 0. But because you have a dependence on set time in many places, as dependence on fees many places, you can actually do EM algorithm. So then basically this becomes a kind of a way. So that Leaders is one of the students here, and she was able to write a paper using a parametric model, and then later Fushike Morikawa extended to non-parametric regression. So now I'm gonna answer the Yumo's question, previous question. So which one is better? So we have two estimators. So MLE, we know MLE is better. MLE is efficient, but optimal method moment estimator also optimal in the class. So the first answer is if you have a parametric model, and if this model is correctly specified, then MLE is more efficient than optimal method moment estimator because it uses more model assumptions. So it uses more assumption. But a second question, if we use a non-parametric model, turns out that the MLE is the arithmetic equivalent to method moment estimator using this one. So it belongs to MOM class, method moment class. So in this case, optimal MOM estimator using 6 is more efficient. But the efficiency, the difference is not really high in the simulation. So that basically take care of the propensity score estimation and parametric model.
Jay, ask another question about the results of the optimal M. So if you go to the page, that's basically the M hat, the estimator, right? Okay.
Here, right?
Right. So in this case, is there any way to do covariance balancing?
Covariance balancing, that is very well.
For 9.
So covariance balancing is really about MAR.
Right.
So if you do covariance balancing, it'll give a biased estimation for on the non-MAR.
Right. So for non-missing at random, we cannot do covariance balancing at all.
If you right, it's not justified, right? So non-MAR. The reason for doing covariance balancing is we want to get rid of the mean part.
Right.
So signal part, right? Signal part and error part. And error part is 0 anyway in expectation. Signal part we want to cancel out through covariance balancing. But I think this is an interesting question. So maybe it's still helpful, but it's not really completely remove the bias.
Okay.
Because the error term is correlation, biased.
Okay, thanks, Jay.
So I think that's probably too much for enough for today. I will this is very short, but I will just skip. Maybe I will cover it over the Thanksgiving break or something like that, or we can just do it after Thanksgiving. Okay, so okay, have a good break, Thanksgiving break, and see you after the Thanksgiving.
Yeah, bye bye. Thanks, Jay.